In this video, we're going to talk about divisibility and modular arithmetic. Now, we're kind of starting a new chapter, and it begins with what a lot of mathematicians know as kind of number theory. So we have this way of relating numbers that looks a little bit different than most. Before we do that, let's kind of get into some basics. If a and b are integers with a not equal to 0, then a divides b if there exists an integer c such that b equals a times c. In other words, a divides into b evenly, and you can write it as a multiplication. The notation we use to represent a divides b is a, and then we do the little straight line and then b. So in math talk, that means a divides b. Okay, so let's kind of play with this notation a little bit. First, let's introduce a theorem that uses the notation. Let's say a, b, and c are integers. If a divides b and a divides c, then a divides b plus c. If a divides b and a divides bc for all integers c. Oh, sorry, then, wow, I said that wrong. If a divides b, then a divides bc, meaning if you multiply b by something, that doesn't matter. A will still divide into it. If a divides b and b divides c, then a will divide c. Okay, we're going to prove this. I'm going to prove the first one and the third one. So let's start with the first one. And we're going to go ahead and assume then that a divides b and a divides c. All right. So if a divides b, that means that b equals s times a for some integer s. Okay. And if a divides c, that means that c equals ta for some integer t. Okay, so that's based on our understanding of what it means when a divides into a number. Okay, well then if I add those two together, b plus c. If I add b plus c together here, I'm going to kind of do it right over here based on this. So b plus c then is going to equal, SA plus TA. So I'm substituting those two things in from those statements. This and this right over here. All right. And then that means that I could factor out A. So this is a times another number, right? S plus T, whatever that is, which means that B plus C is divisible by A. So A divides B plus C based on just that statement, because B plus C equals a multiple of A. That's what this statement here means. It means A times some number. Therefore, A goes into B plus C. All right, let's try the third one. I didn't give myself much space on this, so I'm trying to squeeze it in. Okay, the third one says that A divides B and B divides C. Okay, so A divides B means, again, that B equals SA for some integer S. And B divides C means that C equals T times B for some integer T. It's a little different because we're talking about B dividing into C. Okay, so now using this, C equals T times B, but B equals S times A. So this equals T times S times A. But that means, boop, again, C is a multiple of A. So A divides C. So I can conclude that A divides B plus C and A divides C. And then I'm going to conclude my proof with a little box to indicate that I'm done. All right, there we go. Now, this is a corollary that follows from that theorem directly. If a, b, and c are integers, where a doesn't equal to 0, such that a divides b and a divides c, then a divides mb plus nc for any for some integers m and n. Okay, so we can actually not only just add the two of them together, but we can even multiply them by something and it'll still work, that the a will still divide that. So here's what's kind of cool. This follows just directly from this theorem. Okay, so proof from previous theorem. A divides B and A divides C means that there exists integers m and n where A divides m b and A divides n c. All right, so that's from the previous theorem. That was actually number 2 in the theorem. We didn't prove number 2, but if A divides B, then A divides B times C. All right, so if you multiply something that's divisible by, it's going to work. All right, and then again, also using the same theorem, A dividing these two means that we can add them together. That was from the first one in that theorem. And we're done because that was the conclusion. That's what they wanted. So this corollary followed directly from the theorem. We just applied things from the theorem and we got the result. All right, division algorithm. So this is useful when dividing an integer by a positive integer. There is a quotient and a remainder. This is traditionally called the division algorithm, but it is actually, in fact, a theorem, but we're going to look at it as an algorithm right now. If a is an integer and d is a positive integer, I want you to notice that we're talking about that positive integer, but that's not as important as something else we're going to point out here in a second. Then there are unique integers q and r, where r is between 0 and d. So remember, r is going to be our remainder over here. As you can see, it's a equals dq plus r. So the idea is we can write a number in the form of something we've divided by plus a remainder. So real quick, just really quick, let's say I'm trying to divide, let's do 3 into 7. Okay, so 3 goes into 7 2 times with a remainder of 1. Okay, so according to this theorem, we can say that 7 equals 3 times 2 plus 1. All right, 3 is the magical divisor. And then 2 and 1 are the result of that division. Okay, 2 being how many times 3 goes into 7, and then 1 being the remainder. All right. Important to note that the remainder needs to be a positive number, and it also needs to be smaller than what we're dividing by, right? Otherwise, we could have divided by a bigger number. Another important note is it's actually weird, but it's possible to divide a number by something bigger. Like if I wanted to divide, let's do 4 by 5. So clearly 5 doesn't go into 4, right? It goes in 0 times. I should have used green, sorry. 5 into 4, just trying to be consistent. So it goes in 0 times with a remainder of 4. So we could write 4 equals 5 times 0 plus 4. So when we divide 4 by 5, it has a remainder of 4. And I know that's a little bit weird, but we are going to refer to that later when we start doing the modular arithmetic, and I wanted you to be aware of that. Okay, I'll probably say it again, but let's just kind of understand that basic setup. We can always write an integer in terms of a divisor where it's got possibly a remainder. And it's also possible the remainder is 0. In fact, in all of these, the remainder was 0 because we were saying that our number divided in equally. In other words, the result was just AC, right? There was no remainder in that notation. We were assuming that B equals AC plus 0, meaning our remainder doesn't actually exist in that case. All right, let's come back here. And here is the big definition that we're going to kind of build off of, in particular, the second notation. So in the equality given by the division algorithm, D is called the divisor, A is called the dividend, Q is called the quotient, R is called the remainder. This notation is used to express the quotient and the remainder. So Q, the quotient, can be written as A dividing into D, so A div D, and then the remainder R can be written as A mod D. All right, it's the second notation that we're going to really build on, the modular notation. And I want you to notice that mod notation is talking about a remainder. We're actually doing a process and getting a remainder. We're taking A, we're dividing it by D, and we're saying if its remainder is 5, then that's what we're using this notation to represent, that remainder of 5. Okay, let's use this in an example just to make sure we're good with that. So what are the quotient and remainder when 101 is divided by 11? Okay, so if you try to do 11 into 101, 11 times 9 is 99, right? So it's very close. So 11 times 9. And then if you add 2 to that, that's going to be 101. All right, so according to this notation, then, that means that 9 equals 101 div 11, and 2 equals 101 mod 11. Now, notice I used a parenthesis. That's because the notation used bold, and I can't do bold when I'm writing. So I use a parenthesis instead when I write the notation, just to indicate that I'm talking about modding this remainder. I'm talking about getting this remainder, or div being the division, and we're talking about the quotient. Okay, what are the remainder and quotient when negative 11 is divided by 3? Okay, so negative 11 divided by 3. Here's how we're going to set this one up. So 3, if we're dividing by, so 3 times negative 3 is going to give us, 3 times negative 3 gives us negative 9, right? And then we could minus 2. Okay, now this doesn't work. That actually is not going to work. And the reason it doesn't work is we can't have a negative remainder. Let me do that in blue. Can't be negative. All right, so that one doesn't work. So instead, let's try this. Let's do negative 11 equals, okay, so we're going to overshoot. So I'm going to do 3 times negative 4. That's negative 12 plus 1. There we go. That falls into the qualifications we needed for the division notation we did up here, the division algorithm. Okay, so we were able to write A equals DQ plus R. R is a positive, and so was D, what we divided by, a positive as well. All right, so using our notations then, let's see, negative 4 equals negative 11 div 3, and 1 equals negative 11. Oops, mod 3. All right. Now we're going to kind of abandon the quotient notation, the div notation, and we're going to focus in on the mod notation. So here we go. Definition: if A and B are integers and M is a positive integer, then A is congruent to B modulo M if M divides A minus B. All right, so this is the notation we use for this congruent to B modulo M. All right, we use this notation to represent that. That says A is congruent to B mod M. Now remember, mod M means we're talking about a remainder. So what we're saying is it's possible to divide two different numbers by the same divisor and get the same remainder. All right. For example, if I were to divide, let's say, let's do something interesting. I'm sorry, my brain shut off and it's not very interesting right now. 3 into 7, I think, was one that we did earlier, right? 3 into 7. And that one gives us a remainder of, let's see, 3 goes into 7 twice with a remainder of 1. Okay. If I were to divide 3 into, oh, how about 13? 3 goes into 13 4 times with a remainder of 1. There we go. Okay, so it's the remainders that are equal. We still divided both of them by 3, two different numbers divided by 3, but they had the same remainder. So in this example, A would be 7 and B would be 13. And we're saying that because they both get the same remainder when we divide by 3, they are congruent modulo 3. That's what we're saying. That's what this notation means. All right, let's kind of dive in a little deeper to this. Two integers are congruent modulo M if and only if they're the same remainder when divided by M. Cool, that's what I just said. If A is not congruent, we can write that symbol with the 3 lines with a slash through it. All right. Okay, let's go ahead and look at some examples here. Oh, real quick, I did want to point out that this important theorem does also mention that A is congruent to B modulo M if M divides their difference. So that means we can easily subtract the two things to see if they are congruent modulo M. Let's try. So in this example, let's see if 17 is congruent to 5 modulo 6. So I'm literally going to subtract 17 minus 5. That gives me 12. And I don't know why I'm writing in green, but because this is divisible by 6, that means that 17 is congruent to 5 mod 6. If I divide 17 by 6, I get the same remainder as if I divided 5 by 6. So if I divide 17 by 6, that's going to give me 12 with a remainder of 5. And if I divide 5 by 6, well, remember, when you can't divide the number by 6, the number itself is the remainder. So 5 is its own remainder when we're dividing by 6. So yes, they're congruent. Let's try the next one. So let's do 24 minus 14. Here I'll be consistent. 10. We're also checking for modulo 6. So this is not divisible by 6. So let's use the not notation. That means that 24 is not congruent to 14 mod 6. And there you go. So it's an easy way of checking whether two things are congruent. If you simply subtract them and it gives you something that's divisible by the number, then they have the same remainders. We don't have to go through the process and the work, but I could figure it out if I really wanted to. Sorry, those 3 lines were so uneven. It was driving me crazy. There we go. A little better. All right. In other words, 24 divided by 6, that has a remainder of 0. But when 14 is divided by 6, that doesn't go evenly. So 14 doesn't have a remainder of 0. 14 has a remainder of 2 when I divide it by 6. All right. Okay, let's keep going. Theorem. So let M be a positive integer. The integers A and B are congruent modulo M if and only if there is an integer K such that A equals B plus KM. Okay, so this actually isn't too bad. We're going to prove this. And because they used the phrase if and only if, that means I have to prove it in both directions. I have to prove it where I first assume that A and B are congruent modulo M and then show that the second statement follows that K is an integer such that A equals B plus KM. And then the reverse, I'd have to start by saying, okay, so suppose there's an integer K such that A equals B plus KM, and then show them that they are congruent modulo M. All right, so here we go. Let's do this. let's, when I set this up for ease, I'm going to go ahead and show the direction I'm working. So I'm going to start with the first statement and prove the second statement. So I'm going to start by assuming A is congruent to B mod M. All right. Now, based on the definition, M divides into A minus B by definition. That's the definition above. Okay. Then, because we know that when something is divisible, right? When in the very first beginning, when we have that something is divisible, that means that there exists an integer k such that A minus B equals K times M. Since M goes into A minus B is a multiple of M. And I'm calling that multiple K. Okay, well, that actually, that implies right there, if I solve it for A, if I add B to the other side, A equals B plus KM, I'm done. So that side's done. I've shown that when I assume the first thing, the second thing follows. All right, let's go the other direction now. Let's assume that A equals B plus KM for integer K. I'm not going to write that because it's in the top thing. Okay, well, I'm kind of going in reverse of what I just did a second ago. That means then A minus B equals KM. And now that I'm saying that A minus B is a multiple of M, since A minus B is a multiple of M, M divides into A minus B. And then it follows, wow, that's supposed to be a T. It doesn't look like a T. It follows that by definition then, A is congruent to B mod M by definition. Because we have a definition that says that if it's divisible into the subtraction, they're congruent modulo M. And we're done. We did it. All right. I do want to make mention that when we say equals versus that congruence symbol, they are referring to two different things. This is a relation because in this statement, we are saying that A and B have the same remainder when we divide by M. Whereas here, we're saying that the remainder of A when divided by M is B. So this is a function. It's like the function of division is giving us that result. Whereas over here, we're talking about a relationship between two different numbers when divided by M. Okay, so different ideas are being expressed by those two statements. All right, let's look at another theorem. So we're going to do several theorems and proofs in this, and this is good practice for us as we kind of build towards theorems and proofs. Or I should say good practice on top of doing theorems and proofs. Let A and B be integers. Let M be a positive integer. Then A is congruent to B mod M if and only if A mod M equals B mod M. In other words, that their remainders are equal. Well, we just kind of finished saying that, but this statement kind of just spells it out very straightforward. Thankfully, the proof is very straightforward as well. All right. Now I'm going to prove one way only. And the reason is the homework, you're going to prove the other direction. So I'm going to prove this way. I'm going to prove that if I assume A does equal, I'm sorry, A is congruent to B mod M, that the second statement falls out, that A mod M is going to equal B mod M. All right. So I'm going to assume that they are in fact congruent. Sorry, just kind of making sure that we can see those three lines. Then, so based on the definition, then by definition, there is an integer k such that actually here, sorry, then by definition, sorry. The definition actually says that m divides a minus b. My apologies. Okay, again, by definition, so there is an integer k such that, now I will jump to saying that a minus b equals k times m, which means that actually, I don't even need to say that. We showed earlier that there was a theorem that a equals b plus km. We had a theorem for that. I'm going to call this star really quick because I'm going to refer back to it in a second. Give it a little star. All right. We can also say by the division algorithm, this you don't have to state that it's the division algorithm. All right, I'll put that in parentheses. That doesn't have to be stated. That's me telling you we're using the division algorithm. All right, by the division algorithm, that b equals qm plus r for r being between 0 and m. All right, so that's saying that when we divide b by m, it gives us a quotient and a remainder. Okay, here we go. Substituting what we just did here into the star above. So I'm going to substitute this into b right there. So that's going to give me a equals qm plus r plus km, which equals q plus k times m. So I'm grouping these two together. All right, grouping those two together, factoring out the m plus r. Okay, now this is some new quotient, right? That's just a number times m plus r. So I just put a into this form right there, into that form. Oh, I circled the wrong one. I'm sorry. Into this form using the division algorithm, right? The division algorithm says that a equals, okay, so I just put it in the same form, but here's what's interesting. They have the same remainder. So they have different things that are multiplied by m, but they both have the same remainder, which means I'm done. I've just done it. Therefore, a mod m, the remainder, is equal to b mod m. I showed that they have the same remainder. All right. And you could even take an extra step if you wanted to and kind of say that, okay, so from here, I'm saying, I should say up here, I'm saying that r equals b mod m. And then down here, I could say r equals a mod m. So you can kind of make that statement where you're saying both of them are, that's r. R is representing this modulo notation, and therefore the two things are equal. And there, I showed the one way. Now, technically, I'm not going to close my proof just because we only did one direction. You will be doing the other direction in the homework. All right, theorem. Let m be a positive integer if a is congruent to b mod m and c is congruent to d mod m. You can then add a plus c, and that would end up being b plus d mod m. So adding a and c together gives you the same remainder when divided by m, when you add b and d together and divide by m. All right, they get the same remainder. Same when you multiply. Okay, let's prove it. So let's start by assuming a is congruent to b mod m and c is congruent to d mod m. All right. So then from that, B equals A plus SM, and D equals C plus TM for integers S and T. Integers S and T. All right, so that's based on what we talked about earlier, the theorem earlier, for rewriting something in modulo form into this form. All right. Okay, so that follows then, or I should say it follows from this, that when we add B and C together, that gives us A plus SM plus D plus, I'm sorry, not D, plus C plus TM, all right? And that would equal A plus C plus S plus T times M. Again, I'm grouping the terms with the M's together, right? And factoring out the M. And then I grouped the other terms together. Okay, but that means then now it's in the right form to say that by previous theorem, we can then say that, oh, I just realized that should say B plus D, not C. I'm so sorry. I'm so sorry. I just realized, wait, I used C twice. My apologies. Sorry, that should be B plus D. By previous theorem, then, we could say that B plus D is congruent to A plus C mod, M, which is the statement above, just in reverse. I guess I didn't need parentheses around that. Okay, so we did it. And similarly, wow, that's supposed to have an L. Similarly, there we go. B times D equals A plus SM times C plus TM, which equals AC plus ATM plus SMC plus STM squared. So I'm just foiling. But then that equals AC plus M times AT plus SM plus STM. And again, it's in the right form. So it follows that BD is congruent to AC mod M. Sorry, I had to squeeze it in there at the bottom of the page. My apologies. All right. Boop, little square to say I'm done. I did it. All right, moving on. So let's apply this theorem right down here. So if we know that 7 is congruent to 2 mod 5 and 11 is congruent to 1 mod 5, then we can add those two together. 7 plus 11 should be congruent to 2 plus 1 mod 5. Or in other words, 18 is congruent to 3 mod 5. And that makes sense because 5 goes into 18 15 times with a remainder of 3. And then when you divide 3 by 5, it doesn't work. It just has a remainder of 3. Okay, similarly, 7 times 11 equals 2 times 1 mod 5, which is 77 equals, I'm sorry, this should be not equals, but congruent to 2 mod 5. So basically we're implying, yeah, that they have the same remainder, and they do when they're divisible by 5. Cool. All right, manipulation of the congruences. So we have some ways of kind of manipulating this. If you multiply both sides of a valid congruence, it preserves the congruence. So in other words, if you have A is congruent to B mod M, that implies that AC is congruent to BC mod M. I could multiply both sides by a constant. And actually that follows from the same theorem up here. We would just assume that C and D happen to be the same value. All right. You could add as well using the same theorem, letting C and D be equal. You can add C to both sides and it wouldn't be a problem. However, for division, that doesn't work so well. Okay, so let's look at an example. Let's show an example where it doesn't work. Let's see, 14 is congruent to 8 mod 6. Because if we divide those both by 6, we get a remainder of 2. All right, so they have the same remainder when they're divisible by 6. Okay, now let's divide both sides by 2. Oops, I tried to do that in green and it didn't update yet. There we go, divide by 2 on both sides. So that means I have 7 and 4 mod 6. Now 7 when divided by 6 is a remainder of 1, but 4 divided by 6 is a remainder of 4. So those don't work. Boop. Right? Because when you do 7 divided by 6, you have a remainder of 1. But 4 divided by 6 is a remainder of 4. I'm writing down what I just said in words, right? So they have different remainders. So the remainders aren't equal. That's why this isn't congruent. Okay. There is a corollary about when you mod the mods, when you mod the remainders. And if you add two things together, and take the remainders and add them together and mod them, it works. They end up being the same remainder. It's a little bit convoluted. I'm not going to really go through this. I just went ahead and threw it in because it was in the book and I didn't want to not have it there. All right, there is a arithmetic modulo m. Very interesting. Basically, we can add things mod m and we can times things mod m. So when you add two things, mod m, what you're really doing is you're adding modulo m. All right. So let's look at this. Let's just kind of utilize it. It helps by example. Let's say I want to do 7 plus a sub 11, 9. Okay, so using this notation right here, that means we're using this operator. So according to this, we're going to literally add those together. Okay, so here, let me just rewrite it with a 9. Okay, so according to that, we're going to add them together. So I'm going to actually do 7 plus 9, add those together, mod 11, which is 16 mod 11. So now I'm going to figure out what that remainder is. So if I divide 16 by 11, that's going to give me a remainder of 5, right? 11 goes into 16 once, the remainder of 5. Done. Okay, so let's do the multiplication now. Okay, so again, according to the thing above here, we're going to multiply them. So 7 times 9 mod 11, which comes out to 63. Okay, so if I divide 63 by 11, 11 is going to go into 63 5 times, which is 55. And when I subtract 55 from 63, that gives me 8. So there you go. Those are the answers. 5 for the addition, 8 for the multiplication. And that's how the arithmetic and, the addition and the multiplication work in this arithmetic. Okay, and interestingly enough, they have an associative property, commutative property, they have identity elements. I just listed that here. So they actually have mathematical abilities that we know of, inverses, distribution. It all kind of works with this arithmetic. And there you go.